Welcome everybody. I'm Malte Ostendorf and I'm presenting you the paper with the title Pairwise Multi-Class Document Classification for Semantic Relations between Wikipedia Articles. This is a joint work with Terry Roers, Moritz Schubertz, Georg Rehm and Bela Gibb. With this paper, we present an alternative approach to document similarity. Document similarity is essential to many information retrieval applications like recommender systems. Many digital libraries use content-based recommender systems to recommend literature to their users. These recommender systems generate recommendations based on a similarity measure between seed and candidate documents. So the most similar documents are used as recommendations. But this use of similarity has shortcomings. Because whether two things are similar or not highly depends to what similarity relates. Especially with long documents that cover several topics, two documents can be similar in many different ways. So instead of just measuring one single degree of similarity, you need to rather measure similarity with a context that defines to what the similarity relates. And today's document similarity measures are not really equipped to provide such a context. And that is the reason why with this paper, we propose to solve this problem with a pairwise multi-class document classification. Pairwise means that we have a document pair, let's say A and B, are subject to our classification. And it is multi-class because we have multiple relation classes that describe the similarity of A and B. Also, we consider this a learning problem. So we have positive and negative training samples in form of triple of document A, document B, and a relation R. To test this approach, we use a dataset constructed from Wikipedia articles as our documents and relations from the Wikidata knowledge graph. So the Wikidata properties, we use them as a description of how Wikipedia articles relate to each other. And based on this data, we then can train a model to learn the relation between two articles based on the article text. Now let's have a look at one example. So imagine we have as a seed document the Wikipedia article of Albert Einstein. And now we not only want to find similar articles, but articles with a specific relation. For example, we have the country of citizenship relation or educated at relation. And based on these relation, we then can try to find other articles from persons who have the same citizenship or from persons who were educated at the same institute. But we also then can go and combine several relations. So we could have persons who were educated at the same institute and have the same citizenship. So we construct a data set with 9 relations from Wikidata properties. For example, different from, employer, or opposite of. And we have one additional class, kind of a negative relation or non-relation that represents when two articles are unrelated. In total, we end up with 30,000 samples in our data set. For experiments, we test the following systems. We have 2 transformer models, namely BERT and XLNet. Both are used as they were proposed by their authors. So that's why we refer to them as vanilla transformers, in contrast to Siamese transformers, where we also have BERT and XLNet, but in a Siamese setting. In addition to that, we have 2 word vector-based methods, Dr.vec or paragraph vectors, and document vectors from averaged GloVe word vectors. In the vanilla transformers, BERT and XLNet, we use the sequence pair classification. So both documents are fed into the transformers, only separated with this separator token. And yeah, this is very similar to the next sentence prediction task as used in BERT, for example. But instead of having a binary classification on top, next sentence or not, we have our multi-class classification on top, and that is for the document relation. In Siamese transformers, the documents are independently fed into the transformers, and the representations are concatenated before the classification layer. Here, the difference to the vanilla transformers is mainly that instead of a single, we have two independent transformer blocks. That means that we also have double the input length for each transformer. So to see how this change in input lengths affects the performance, we evaluate different models with different input lengths in our experiments. Similarly, the concatenation is also subject to our evaluation because as today, there's no clear best practice in how to handle concatenations in Siamese transformer networks. So we test different concatenation to find out what is the best for our approach. The word vector-based methods, Dr.Vec or average glove, work very similar to the Siamese transformers. But instead of having a transformer here and there, we use the representations from Dr.Vec or average glove vectors. And the difference from the word vector-based methods to the transformer methods is that the input documents are not bound to any kind of input lengths. So Dr.Vec and average glove can both utilize the full article text. But for further implementational details, please look into our GitHub repository. We have all our code, dataset, and models available there. All right, let's look into our results. Vanilla BERT achieves the highest microF1 score, closely followed by vanilla XLNet. Then we have the word vector-based method, average glove, and next the two Siamese methods, Siamese BERT and Siamese XLNet. And the worst performing method is Dr.Vec. In a model-wise or category-wise comparison, we see that the vanilla transformers yield the best results, followed by the word vector-based method, average glove. And then we have the Siamese models. So even though the Siamese models are computational more complex than the average glove outperforms them. And we attribute this to the fact that the input length for the Siamese models is limited, whereas average glove can utilize the full article text. On the other hand, we see that BERT outperforms XLNet in the Siamese and in the vanilla version. And this is mainly due to the fact that XLNet is pre-trained on additional web corpora. So it's not as focused on the Wikipedia during pre-training as BERT. And also, XLNet does not make use of the next sentence pre-training objective, which, as we said earlier, is very related to the task that we are doing here. And that's why we see BERT outperforming XLNet. But how do the methods perform on different relation classes? Here in this table, we see on top the different methods. And on the left column, we see the different relation classes. The best relation classes in terms of performance are country of citizenship, different from, and the non class. So the articles are unrelated in this class. In contrast to that, we have as worst performing classes, employer, has effect, or has quality. Given that the best performing classes are also overrepresented in terms of sample count, this is what you can see in the right column, we can state that more training data improves the performance. But the performance differences among the classes is also due to the different requirements of the classes themselves. So one example is the employer class, which yields a relatively low F score while still having comparable high sample count. And this is due to the fact that the employer class is very similar and hard to distinguish from the educated at class. So imagine in the Albert Einstein example, Albert Einstein could have been educated and employed at the same organization. So this makes it really difficult to distinguish between the two classes. And it's the reason for those results. Aside from our quantitative analysis, we also analyzed manually samples to get a better understanding on how the models actually perform. So here we have a seed document, a target document, and the relation as defined by Wikidata, and the predictions by vanilla BERT. And when we look at the samples, we see on one hand that in some cases, the Wikidata information is not reflected in the Wikipedia articles. So for example, the article of Rudolf Moradane mentioned that Armenia is his country of citizenship, and that's why also kind of this prediction happens, but that Brazil is also his country of citizenship is nowhere mentioned in the article. And that's why the model predicts none, because Brazil is never mentioned. At the same time, we see that the task can be difficult to achieve since the labels are quite fuzzy. So when you see light and darkness, you all probably can agree on that opposite of is a correct relation between the two. But similarly, you could also argue that darkness might be a quality of light. So this fuzziness shows that it's really difficult to learn this task. So to conclude, in our experiments, and we showed that in addition to this standard similarity measure, we can learn a semantic relation between documents with a pairwise document classification task. We tested our approach with Wikipedia articles and Wikidata properties. Vanilla BERT achieves the highest microF1 score and above 90%. Siamese transformers did not achieve an as good as performance as average graph, while average graph is requiring less computational resources than transformers. Moreover, we found that these semantic relations allow a more fine-grained similarity assessment, and they provide additional context information, what the two documents have in common. And this finding motivates further research in this direction. In particular, we want to find out whether our findings can generalize to other corpora. So we acknowledge that Wikipedia and Wikidata that we use in our experiments are kind of special in the sense that all the articles represent entities, and the relations between the two entities are also explicitly expressed in most of the text. So the question remains whether this can also be shown or used for other corporas. So currently, in the follow-up work, we are applying this approach to research paper to find out whether also it would work there with more generic relations like background, method, and which are not really focused on entities. But these results will be published in a separate paper. All right, thank you very much. I hope you enjoyed the talk. Our code, dataset, and pre-trained models are all available on GitHub, including a Google Colab demo. So thank you very much.